We're going to look at intermolecular forces and pure liquid properties. Later we'll be talking about mixtures. We're going to look at the process of vaporization, vapor pressure, boiling point, interpreting vapor pressure curves, capillary action, surface tension, and viscosity. Let's first look at the process of vaporization. We have here a Maxwell-Boltzmann distribution diagram. For vaporization, the liquid particles have to have enough kinetic energy to overcome the liquid phase IMFs and escape into the gas phase. So for the low temperature sample, only this small fraction of sample down here has enough energy to escape. As we increase the temperature, now we have a greater fraction of molecules that can escape. Vapor pressure is the pressure exerted by a liquid or solids vapor, and we're going to be looking at liquid, in a closed container once equilibrium is reached. So up here we would be able to measure the vapor pressure. So we said that vapor pressure increased as temperature increases. So here we have ethanol, and it doesn't say here, but this is at 0 degrees Celsius. And we can see that very few molecules are in the gas phase, and we only have a vapor pressure of 1.63 kPa. As we increase the temperature, a greater fraction of the molecules down here can escape and get into the vapor phase, so our vapor pressure increases. Boiling occurs when the vapor pressure equals the external pressure. So atmospheric pressure in this case would be our external pressure. Initially, as we heat a liquid up, you'll see a little tiny bubble starts to form. However, the pressure coming from the atmosphere is greater than the pressure inside the bubble, the vapor pressure, and the bubble just collapses. Once the internal pressure in the bubble is equal to 1 atmosphere, now the bubble can keep expanding and go to the top of the surface. Here's another image of what I was just talking about. You can think of atmospheric pressure as the arrows pointing down, and then the vapor pressure is the water molecules and their effort to escape from the liquid. Once they match, boiling will get vigorous. Let's take a look at interpreting vapor pressure curves. This shows temperature on your x-axis and vapor pressure in torr, that is the same thing as millimeters of mercury, on your y-axis. And we have 4 liquids here: diethyl ether, ethyl alcohol, water, and ethylene glycol. This line right here represents what's called the normal boiling point. That's 1 atmosphere. So we can see that we go from 34.6 degrees as the boiling point of diethyl ether, and ethylene glycol we can't even see. That's going to be way off the graph somewhere. So let's take a look at this. The question is, what is the boiling point of water at 600 millimeters of mercury? So we find 600 millimeters of mercury. We go across to where we intersect the line for water. We go down, and it looks like it's somewhere around 93 degrees Celsius. Now, if we look at these curves, which liquid would you expect to evaporate most quickly at 25 degrees Celsius? Well, at 25 degrees Celsius, we're about right here. And so what we want is the one that has the greatest vapor pressure. So as we go up, we go, okay, and that's going to be the diethyl ether. We'll just say that's the red line, okay? Now, which liquid has the smallest intermolecular forces? In other words, which one escapes the easiest? So that would be the liquid with the highest vapor pressure, which would again be the diethyl ether. Let's take a look at another vapor pressure curve. This is a set of alkanes, C5H12, C6H14, C7H16, C8H18. All of them are nonpolar because all we have are CH bonds. which means that the only thing that is going to determine their relative IMFs is the London dispersion forces. We would expect the molecule with the fewest total electrons to have the lowest boiling point, and that is indeed the case, with the number of highest total electrons having the highest boiling point or the highest vapor pressure at any given point. Well, let's try another question here. What is the boiling point of C6H14 at 300 millimeters of mercury? Well, we find 300 millimeters of mercury, intersects the line there. Then we go down to the x-axis, and it looks like it's about 42 degrees Celsius. Let's take a look at a couple of others, or a few other properties: capillary action, surface tension, and viscosity of liquids. And these are all based on IMFs, intermolecular forces. So capillary action occurs when a liquid rises up a thin tube due to a combination of adhesive and cohesive forces. Cohesion is the attraction of liquid molecules for each other. You can think of it as two people wanting to hold hands. Adhesion is the attraction of the liquid molecules for the tube wall. So there's another drawing of it. Cohesion here, how attracted the particles are to each other, and then adhesion, attraction between the wall and the particles. When the adhesive forces exceed the cohesive forces enough to overcome the forces of gravity, the liquid rises up the tube and the meniscus is concave. Such is the case for H2O. Mercury is very different though. Mercury has very strong cohesive forces because the attractions between the Hg particles are metallic bonds, and those are much stronger than the IMFs between molecules. So now we actually see that it's a little below the level of the liquid on the outside. There's a lab that under normal circumstances we could do that depends on capillary action, and that is called paper chromatography. If we put a sheet of paper into some water, and we've got a drop of ink on it, so we put it down in the water, so this would be our water level. What's going to happen is the water is going to travel up the paper by capillary action, and it will actually separate the various dye components by their interaction of the IMFs between the ink, paper, and the solvent. Last one we're going to look at is surface tension. So if we're looking at a droplet on a surface, well, that's a better drawing right there, okay? The molecules or atoms on the surface feel attraction forces only to one side, and thus they're going to be drawn in towards the liquid. If they're in the center, they're being attracted to all the particles, and so they're clinging together very tightly. So the stronger the attraction, the more sphere-like the droplet will look. Again, liquid mercury has a very high surface tension because the particles are attracted by metallic bonds, and those are much stronger than the IMFs between molecules. Viscosity is a liquid's resistance to flow. So what I want you to think is syrup. When you put syrup on your pancakes, syrup is viscous. And you may have noticed it gets less viscous as you heat it. The stronger the IMFs you have, the more viscous the liquid is. So here you see very weak IMFs, and this has very strong IMFs.